Welcome to G Fun Facts Online. Today we are going to talk about a breakthrough that sounds like it was ripped straight from the pages of a science fiction novel. It is the story of how a simple ingredient found in Doritos and Mountain Dew has unlocked a new superpower for biologists: the ability to turn skin invisible. Let's start with a simple experiment you have probably done as a child. If you go into a dark room and press your hand against a bright flashlight, what do you see? You see a dull red glow. You are seeing light pass through your body, but you are not seeing through your body. You cannot see the bones of your fingers. You cannot see the intricate web of veins or the pulsing of your arteries. You see only a diffuse, scattered blur. For centuries, this has been the fundamental wall-hitting medical science. The human body is not a window, it is a curtain. To see what lies beneath, we have had to cut, radiate, or scan with expensive, bulky machines. But in September 2024, a team of researchers at Stanford University shattered this wall. They did not use a new billion-dollar particle accelerator. They did not use a futuristic genetic editing tool. They used a yellow powder found in your kitchen cupboard. By rubbing a solution of Tartrazine, which is the common food dye FD&C yellow number 5, onto the skin of a living mouse, they made the tissue optically transparent. For the first time in history, scientists could watch the neurons firing in a living brain and the intestines digesting food simply by looking through the skin as if it were a pane of glass. This is the story of the Tartrazine window. We are going to explore the physics that made it possible, the century of failed attempts that preceded it, and the medical revolution it promises to unleash. To understand why this discovery is so profound, we must first understand why we are not already transparent. Biologically, we are made mostly of water. Water is clear. The lipids, or fats, and proteins that make up our cells are also, on their own, relatively clear. So why, when you mix them together, do they become an opaque barrier? The answer lies in a concept called the refractive index. Imagine driving a car down a highway. If the road is smooth, you travel in a straight line. Now imagine the road is patched with piles of thick mud. Every time your wheels hit the mud, they slow down and your car jerks to the side. Light behaves the same way. When it travels through a material, its speed is determined by that material's refractive index. Water has a low refractive index of about 1.33. Fats and proteins, however, have a high refractive index, ranging from about 1.44 to 1.50. Our tissues are a chaotic mixture of these two things. As a photon of light enters your skin, it passes from water to fat to protein, and back to water. At every single interface, the speed limit changes, causing the light to bend, or refract, and bounce or scatter. Multiply this by the billions of cells in your skin, and the light is scattered in every direction. This is what creates opacity. It is the same reason why a crushed ice cube looks white and opaque, even though the individual ice crystals are clear. The light is getting lost in the thousands of transitions between ice and air. In H.G. Wells' famous 1897 novel The Invisible Man, the protagonist Griffin invents a serum that changes his body's refractive index to match that of the air. If the refractive indices match, light doesn't bend, it passes straight through. The Stanford team, led by assistant professor Guosong Hong and lead author Zihao Wu, realized they could not lower the refractive index of human fat to match water, but perhaps they could raise the refractive index of the water to match the fat. This was the counterintuitive brilliance of their approach. Usually, when we think of dye, we think of something that blocks light. We use sunglasses to block glare. We paint walls to hide what is behind them. But the Stanford team used a dye to allow light to pass. The science behind this involves a principle of physics known as the Kramers-Kronig relations. These mathematical equations describe the connection between how a material absorbs light and how it bends light. The relations state that if a material absorbs light very strongly at a specific color or wavelength, it will dramatically change the refractive index of the material at neighboring wavelengths. Tartrazine is a scattering killer because it is a master of this relationship. First, tartrazine is a deep yellow-orange dye. This means it aggressively absorbs blue and ultraviolet light. Second, because it absorbs blue light so intensely, the Kramers-Kronig relations dictate that it must drastically raise the refractive index for red light. Third, when dissolved in water, the tartrazine raises the water's refractive index to approximately 1.44, bringing it into perfect alignment with the lipids in the skin. Suddenly, the mud on the highway is gone. The water and the fats now treat light exactly the same way. The light stops scattering. To the human eye, the skin turns a deep red color because the blue light is absorbed, but it becomes transparent. You can look right through it. The researchers started small, using thin slices of chicken breast. As they increased the concentration of tartrazine, the chicken meat, which is normally pink and opaque, gradually vanished, leaving only a clear, reddish jelly. They could see the text of a grid placed behind the meat with perfect clarity. Then, they moved to live mice. The results were nothing short of science fiction. They applied the tartrazine gel to the scalp of a mouse. Within minutes, the skin became invisible. The researchers could see the blood vessels zigzagging across the surface of the brain. They could watch the blood flow in real time, observing the brain's microscopic plumbing without removing a single piece of bone or skin. This transcranial window is the holy grail for neuroscientists who currently have to perform invasive craniotomies or skull-thinning surgeries to see the brain. Next, they rubbed the solution on the mouse's belly. The abdominal skin faded away. Beneath it, the liver, the bladder, and the intestines appeared. They could see peristalsis, the rhythmic muscle contractions that push food through the gut. They could literally watch digestion happen. They could see the mouse's heart beating and its lungs inflating, all through the closed window of the skin. Crucially, the process was reversible. When they rinsed the mouse with water, the dye washed off, and the skin returned to its normal opaque state. The mouse suffered no ill effects. The invisibility cloak was temporary, safe, and completely non-surgical. To appreciate the elegance of the Tartrazine solution, we must look at the messy history of tissue clearing. The quest to make flesh transparent began in 1911 with Werner Spalteholz, a German anatomist. He discovered that by soaking dead tissue in oils like methyl salicylate or wintergreen oil, he could make it translucent. However, the process was harsh. It required dehydrating the tissue with alcohol, which shrank and damaged it. It was strictly for dead specimens in jars. For the next century, scientists refined this chemical clearing. In the late 20th century, we saw BAB, a mixture of benzyl alcohol and benzyl benzoate. It was a powerful clearing agent, but toxic and destructive to fluorescent proteins. In 2013, another Stanford breakthrough called Clarity replaced the lipids in the brain with a clear hydrogel. It created stunningly transparent brains, but the animal had to be dead, and the process took weeks. These methods were optical clearing via removal. They worked by stripping the fat out of the body. The Tartrazine method is optical clearing via addition. It leaves the body intact and alive, simply adding a temporary molecule to balance the light. It is the first time we have achieved high-quality transparency in a living mammal without genetic modification or surgery. Now let's talk about why this changes everything. The implications of the Tartrazine window extend far beyond looking at mice. This technology represents a fundamental shift in how we might diagnose and treat human disease. Consider the end of blind blood draws. We have all experienced the discomfort of a nurse poking a needle around, trying to find a vein. For the elderly or infants, this can be a traumatic ordeal. A Tartrazine-based lotion could be rubbed onto the arm, making the skin transparent and revealing the veins in high definition. A phlebotomist would never miss again. Think about early cancer detection. Melanoma is the deadliest form of skin cancer, often because it grows deep into the tissue before it is noticed. Current screening is limited to what is visible on the surface. With optical clearing, a dermatologist could look into the skin, spotting suspicious tumor roots or abnormal blood vessel growth long before they breach the surface. It could allow for optical biopsies, where a doctor diagnoses a tumor by looking at it directly, rather than cutting it out. Then there is the laser therapy revolution. Lasers are used for everything from tattoo removal to killing cancer cells. However, skin scatters the laser beam, diffusing its energy and limiting how deep it can reach. This is why tattoo removal is painful and requires many sessions. The laser is fighting the fog of your skin. By making the skin transparent first, the laser beam could travel straight to the target, whether it is ink pigment or a deep-seated tumor, without losing power. This would make treatments more effective, faster, and less damaging to the surrounding healthy tissue. We could also see a change in monitoring digestive disorders. Irritable bowel syndrome and Crohn's disease are notoriously difficult to monitor because the gut is hidden. Doctors rely on indirect symptoms or invasive colonoscopies. With a transparency technique, we might one day be able to monitor gut motility simply by applying a solution to the abdomen, watching how the intestines move and react to different foods or drugs in real time. Of course, we must address safety and the hurdles ahead. Is it safe? Tartrazine is FDA approved. Millions of people consume it every day in colored drinks, candies, and chips. The researchers found that after the experiment, the mice simply excreted the dye in their urine within 48 hours. There was no inflammation, no toxicity, and no long-term change to the skin. However, there are hurdles to crossing the species gap to humans. The first is skin thickness. A mouse's skin is paper thin. Human skin is at least 10 times thicker. Simply rubbing Tartrazine on a human arm might not penetrate deep enough to clear the dermis fully. The second hurdle is the delivery method. To work on humans, the dye might need to be injected or delivered via microneedle patches, which are essentially microscopic needles that dissolve in the skin, to get the dye deep enough to match the refractive index of the thicker collagen layers. The third hurdle is the color. The dye makes the skin red. This means you can only see through it using red or near-infrared light. You would not see true color beneath the skin. You would see a monochromatic red image. However, for medical imaging like seeing blood vessels, contrast is far more important than color. The Tartrazine window opens up a new field of in vivo optical clearing. Researchers are already screening thousands of other FDA-approved molecules to see if others work better, penetrate deeper, or work at different wavelengths. Imagine a future where a transparency patch is a standard item in a first aid kit. In the field, a combat medic applies a patch to a soldier's chest to instantly locate internal bleeding or shrapnel without needing an ultrasound. In the lab, pharmaceutical companies test new drugs by watching them absorb into organs in real time, drastically reducing the cost and time of drug development. At home, a diabetic patient uses a small optical device to check their blood sugar by looking directly at the glucose levels in their interstitial fluid. No needles required. The Stanford team has proven that opacity is not an immutable law of biology, it is a variable. And with a little bit of yellow food dye, we have learned how to turn the dial. We are entering an age where the body is no longer a black box, but a glass house. The invisible man is no longer fiction, he is the future of medicine.